Welcome to the National Geotechnical Centrifuge Facility, NGCF, located at the University of Western Australia in the beautiful city of Perth, Western Australia. The NGCF supports the geotechnical physical modelling work of the Centre for Offshore Foundation Systems, or COFS, located in UWA's Oceans Graduate School, and of the geotechnical group within the Department of Civil, Environmental and Mining Engineering, and numerous collaborating partners around the world, both in academia and in industry. The genesis of our work originated in the oil and gas developments off the northwest shelf of Australia back in the 1980s, where the problematic carbonate seabed deposits posed significant engineering challenges. The geotechnical efforts that ensued included geotechnical centrifuge modelling at UWA dating from 1988. We have built from those foundations and now tackle a wide range of geotechnical engineering problems, both on and offshore, with our main focus on solving geotechnical engineering issues associated with the deployment and operation of offshore wind and wave energy devices. The NGCF is made up of a team of research officers, mechatronic, electronic, software and mechanical engineers that have unique skills and expertise in geotechnical centrifuge modelling. This dedicated team leads the technical developments within the facility and facilitates the research that we produce. I trust you will enjoy seeing our facility, and I look forward to welcoming you to the NGCF, either virtually or in person.
The NGCF boasts a heavy arsenal of state-of-the-art geotechnical modelling tools, all housed in a 700 square metre laboratory in the Indian Ocean Marine Research Centre at UWA. The NGCF operates 3 geotechnical centrifuges, a comprehensive suite of single gravity testing stations, and state-of-the-art online control terminals featuring remote access and control and live streaming of data to clients and collaborators all around the world. The centrifuges are heavily utilised with a balance of academic and industry projects, spinning up to 300 days per year. Commissioned in 1996, the drum centrifuge has a diameter of 1.2 metres and can reach an impressive 400 G. Heavily developed in-house, the already capable broadbent platform was upgraded with a custom-designed VHM actuation system that has been used to quantify the capacity of shallow foundations, such as the spud cans on a jack-up leg under combined loading. The twin concentric shaft design allows the central tool table of the NGCF drum centrifuge to be actuated in flight to access the almost 4 metre long sample surface. This aspect has historically lent itself to parametric studies of penetrometer and spud can penetration, drag anchor testing, and more recently for investigating submarine debris flow and tailing dam stability. The Actidon C661, or small beam, is a 40 G-ton beam centrifuge capable of spinning a sample weighing up to 200 kilos to an acceleration of 200 G. Installed back in 1989, this centrifuge has proven its worth and reliability over an impressive 30-year lifespan and is still going strong. In 2016, this centrifuge was relocated to the new Indian Ocean Marine Research Centre where it resides today. The centrifuge's 3.6 metre diameter allows for easy and efficient operations such that it manages a very high throughput of projects each year. The NGCF builds on the Actidon platform using bespoke robotic actuation to simulate real-world events and fully custom digital data acquisition measuring up to 64 channels of sensor data ranging from forces and pressures acting upon the model to nanometer displacement measurements tracking the movement of the foundation within the seabed. Installed in 2016 to coincide with the opening of the IOMRC, the Actidon C72 Big Beam centrifuge shares a similar design philosophy to the C661, but on a much more massive scale. Weighing in at over 20 tonnes, this 10-metre diameter machine is capable of spinning a 2-tonne payload at 130 times Earth's gravity. At full speed, this is similar to the weight of a Boeing 787 circling the enclosure at over 350 km per hour. In order to safely contain such a huge kinetic energy, the enclosure is made of solid concrete 1.5 metres thick with 20 mm steel reinforcement. The large beam is powered by 2 220 kilowatt electric motors coupled via a belt to a central drive wheel. As a modern centrifuge, it also has in-flight automatic balance adjustments, vibration monitoring, pre-programmed acceleration profiles, and an open platform to install NGCF designed hardware quickly and efficiently. In all, the 3 centrifuges are complementary to each other. The linear testing length of the drum allows for parametric type studies, modelling run-out events, and is utilised in undergraduate teaching programs. The The smaller beam is a highly efficient machine, providing an optimal balance between adequate testing volume for most modelling problems and fast throughput. Finally, the larger beam allows for much larger soil samples, or a number of separate samples to be tested at once, and provides the real estate needed for more complex actuation and physical models. To support the smooth operation of the centrifuges, the NGCF operates a cutting-edge single-gravity lab. The lab features 4 fully equipped stations, each with the same motion control and data acquisition systems as found on the centrifuges. This allows the researchers to prepare for their experiments using the same testing environment as in the centrifuge, providing them with a means of refining and validating their experimental arrangement and procedures before moving on to the main event in the centrifuge. The result is a best-in-class efficiency with excellent throughput of high-quality data. In some instances, the correct physical modelling approach is to test in a single-gravity environment. Here, the technical team collaborates with academics and students to design a robust series of experiments and is involved with the whole life cycle of the project from initial concept design, model fabrication, and test execution. Finally, the NGCF has a variety of tools at its disposal to create and reconstitute a wide range of soil samples. The bespoke sand renner is used to create sand samples to predetermined relative densities, whilst the vacuum clay mixer and 2 consolidation presses can apply loads of up to 350 kilonewtons, equivalent to almost 1.5 MPa in our smaller centrifuge strongboxes. The lab routinely also works with natural offshore soils, supplied courtesy of our industry partners. These are reconstituted and subsequently consolidated or densified to a target in situ state using a combination of loading in the consolidation presses and in-flight consolidation in the centrifuges. The in-house electronics team specialise in designing, developing and manufacturing the bespoke hardware and software used in our centrifuges and single gravity testing stations, and in instrumenting the reduced scale physical models. They have the difficult task of making sure the equipment can survive the harsh conditions in the centrifuge, not to mention the macro-G environment, and are available to undertake last-minute alterations and repairs during testing, minimising downtime on the centrifuge. The electronics team have developed tools, motion control and data acquisition systems to suit the requirements of geotechnical centrifuge modelling. Examples include DigiDAC data acquisition, Mars PAX motion control system, actuators, T-bar and piezo cone penetrometers, load cells and bending legs. The equipment is well utilised by the NGCF, but is also sold to other physical modelling centres all around the world. The NGCF's mechanical engineer works closely with the NGCF users to design the intricate centrifuge models and onboard equipment, with the centrifuge operators to design ancillary equipment for the centrifuge, and with the electronic engineers to accommodate instrumentation in the centrifuge models. A further and key responsibility is the provision of immediate maintenance and modification to centrifuge equipment and models to ensure maximum productivity of the facility. There is a long history of geotechnical centrifuge modelling at UWA, from our beginning in the late 1980s supporting offshore energy production on the northwest shelf of Australia to current activity which is supporting the transition and growth of offshore renewable energies globally. We invest in and support our technology and our people to allow us to generate research that makes a difference to how engineers design, install and monitor offshore infrastructure.